So thanks for coming to this this short talk. By about 10 o'clock, with time to spare, ideally, I hope to have provided an answer to these questions, which is how we can categorize explainable and interpretable AI techniques, whether we can trust explanations of AI models, whether explanations can be fooled by adversarial attacks. This is the kind of different variant of adversarial attacks to what the term normally means in machine learning. And lastly, we'll touch on how we can gain confidence explanations are actually robust and accurate. But before we do that, I should probably say who I am. I'm Michael Pidgeon. Here's a topical photo. I quite like the idea of someone stumbling across that in a few years on YouTube and thinking, what the hell is that on his face? But I'm here to do a one year master's in AI at Heriot-Watt, and Katya has very kindly agreed to supervise my dissertation on explainable AI robustness, or some variant of that. The details, I can only apologize, Katya, for the number of times the details have changed, but it's something in that space. So yeah, there'll be a couple of demos.
Apologize, by the way, Michael. That's absolutely
Okay.
fine.
Oh,
it's your job to change opinions and grow. So that's
yeah. Oh, good to know, Katya. So the way I'll do this is there's those 4 sections. I'll pause at the end of each sections and do my best to to answer any questions. The first 3 sections I should be able to hopefully answer questions reasonably confidently. The last one is a bit more ideas of how we can answer that question of our explanations robust. But we'll see how we get on. So the first section then is actually just a bit of a primer on interpretable and explainable AI, and so we'll just go through some sort of very basic terms, what we mean. So by a model, no surprises here. We just mean any machine learning model mapping input features to outputs. And it's just important to note that we don't exclusively mean neural networks or CNNs or any particular type of model. It can apply to these explanation techniques, can apply to any type of machine learning model. And by explanation, in the broadest sense, we just mean some mechanism of establishing why a model gave a certain output. And we often see images like this in explainable AI papers, where we can see here that there's certain pixels identified as being more salient to particular classifications, and we could also do that for nominal data too. We don't see this kind of thing quite as much in the literature, perhaps because they don't look quite as immediately interesting. But this type of data is obviously really important. This is the census salary prediction data set that people are probably familiar with, and we can see at the bottom we've got sex and race there as features, with sex actually used to influence the prediction to a small extent. So we're immediately thinking about bias, and let's hold that thought, because we'll come back to it later. So a quick note on interpretability versus explainability. So this here is my preferred definition of these 2 terms, which is that models are those which are intrinsically explainable. So those that we don't have to do anything whizzy to be able to explain and understand them. So simple linear regressions or decision trees and that sort of thing. Whereas explainability is where we actually use some sort of alchemy to communicate the function of a more complex machine model to users. There are other definitions of interpretability. Sometimes it means a more technical explanation of a model, and often these, to be honest, are used quite interchangeably. So there's a little bit of caution needed. So when we search for something like AI explainability on Google Scholar, we're presented with a large number of review papers, which are all very helpful, and they all contain some variant of this diagram, which attempts to give a taxonomy of different explainability techniques. Now you'll be relieved to hear I'm not going to go through this in any level of detail. However, I would like to highlight a couple of the more interesting distinctions. The first area, and I'm going to try and get some money's worth out of my Wacom tablet here. The first is this transparent models section at the top. And these broadly align with that idea of techniques which are inherently interpretable, which I spoke about before. So simple linear regressions, decision trees, that kind of thing. And notice the word can there. These can be inherently interpretable. And that's not always the case. You know, clearly, if we have a decision tree with 10,000 leaves and nodes, that's not going to be interpretable without the use of any other techniques. Sometimes these are called anti-hoc techniques as well. The second category is the post hoc explanations, which is the second kind of broad split. And really, what we mean by this is, yeah, again, it varies slightly, but what we always mean is attempting to explain results using the model outputs. Normally, we mean a specific decision we're looking to explain, so a local explanation as opposed to a global explanation. And often we do this by using a separate model, so called a surrogate model. We'll see here that these divide into model agnostic and model specific techniques. I'm going to focus on model agnostic techniques in this talk, just because I think they're the more interesting, and also the more relevant, the more useful, because in practice we quite often don't have access to model internals. This is this black box idea. We might not have access to gradients and weights, and sometimes we might not even know the type of model that we're using. So these techniques obviously come in quite handy. So the conclusion for this first little section is that, you know, it's a very new area, developing very fast. As you'd expect, the definitions are a little bit shaky. I've maybe been a bit cynical there. No definitions for practically anything. It is a new field, but we do need to probably understand the details of any specific technique. We can't really rely on the way that someone else has classified it. Of course, there are attempts to kind of standardize the language, but you know, we tend to end up with this problem where, you know, another set of standards in language emerges, which can sometimes add further confusion. So so that's a whistle-stop tour of the of explainable AI and the broad splits in the different techniques. I'll just pause for any questions.
Just a comment, Michael. This division between explainable and interpretable is really nice. I haven't come across it, so well done. It does make sense when you say it.
Yeah, it's definitely the most useful, the most intuitive, but also the most useful definition, because we often find that explainable techniques work, and we will see this in a minute. They work by developing an interpretable model. So it's definitely the definition that I find the most useful, and it is the one that people seem to be standardizing on, as far as I can tell.
And there's a question for you in the chat. What is user?
All right.
I'm not sure what it refers to.
This is, we were just talking about this, weren't we? The chat and what is user. I'm not sure what. Oh yeah, I don't know what that means. So that was just a couple of minutes ago. So let me just skip back quickly on my slides. What did we mean by that? I don't know if Priya, if you wanted to just I don't really know what that means. If you want to clarify, I'll come back to that quite happily. So let's go on to this question of can we trust these post hoc explanations of AI models? We know now where post hoc methods sit in that taxonomy. So let's look at an example of those and how they actually work. Specifically, we'll look at LAIV and Shap. These are probably the two most popular and widely used explainability methods, and it seems to me that Shap is actually starting to overtake LAIV in popularity. But they both essentially work in the same way. They're both local surrogate methods. They attempt to explain a result for a single instance. They do differ in how they execute these three steps, but the principles are the same. they construct a separate function, a surrogate function, that attempts to be locally faithful to the original model. So in other words, should behave the same as the original model in the locality of the instance that's been picked. So this is how it works very quickly. So first, we take an instance. We choose a specific point. So in this case, we've chosen this bold cross here. And then we then modify that instance. We perturb it multiple times, and we can see that here these points where we've selected. And this is actually the main difference between LAIV and Shap. LAIV does this almost randomly, whereas Shap is a bit more methodical and sort of mathematically robust in how it does that. We then run these instances through the model, which gives us results, and we weight those results according to the distance from the original instance, normally by a Euclidean distance. So we know now these are this circle class, and these are crosses, and we know that the sizes here are different too. And then what we do is we take that data we've generated and we use that to train a new interpretable model. And this is where the whole explainability and interpretability thing comes in quite useful, because we know now what an interpretable model means. This is one that's using simple, not simple technique, but an interpretable technique. So often this is a linear regression model, or a simple decision tree, or something like that. And we can see that split here. So what I'll do is I will switch to doing a short demo of this. If I can work out how to come out of PowerPoint. There we go. Let's stop that from blinding me. So I'm going to do a really short demo of Shap. Just what it. I'm not going to get too into how it works, but just a short demo of what this looks like in practice. So we've got a simple Jupyter notebook here. So the first few bits of this I'll skip through. We're just importing some dependencies, and we're going to use the iris data sets here.
Michael, sorry, may I interrupt you? Could you make font bigger?
Oh, of course I can. Yeah,
if you expect us to see the code.
Yeah, thank you. Thank you. Is that okay like that?
It's okay to me, but I'm not sure how everyone.
I'll do one more just to be on the safe side, and I'll close this thing down too if I can. There we go. That's better, isn't it? Thanks, Katya. So we train a classifier on this iris data set. Here it's a random forest classifier, but that doesn't really matter. Any classifier would work. And as we're expecting, we get a high accuracy here, given this is it's a very simple data set. What we then do is we actually use Shap to explain the test set predictions. So generally we're just we look at it instance by instance, but there is a method we can look at all instances at once. But that takes a bit longer, so we get this warning. But for iris, we can get away with it. And now we can actually see some explanations. So if we look at the first couple of instances in our test data set, first label for that is 2, and the first is 1. I'm not actually sure what they correspond to. But if we say here, we're just saying here we want to explain the first instance, and we want to explain why that is label number 2. And we do that, and we get a diagram that looks a bit like this. Look quite nice, these visualizations you get out of Shap. But we can see starting from a base value, which is somewhere between 0.3 and 0.4. These are the main features which actually push it towards it being truthy for label number 2. And we can see equally, we can reverse that, and we can say why is it not label 0. Here it's more or less an exact mirror image, as we'd expect given the simplicity of the data set, but it might not necessarily be with more complex data.
Michael, may I interrupt you? Could you scroll for any? Yeah, so what should I, we're explaining just one instance, one flower, picture of one flower. So how should I understand this graph? That picture was classified with label 2 because?
Well, the picture is classified as label 2 because of these features. So what we're saying here is an output value of 1 suggests that yes, that is it's a bit like a one-hot encoding sort of idea. That instance is classified as label 2, and every one of these explanations starts from some average base value, which is between 0.3 and 0.4, and what we can see is these are the features that actually push it in that direction and contribute more to the classification. So we can see that the features that contribute the most are petal width and petal length.
Okay,
with
so the size of this bar essentially.
Yeah, exactly.
Mm-hmm.
Exactly. And we can actually see if we explain the second instance, this might actually help, because here we can see that we're actually not quite as certain in here. So we're attempting to explain why this is label number 1 here. I probably should have actually mapped these to the what these mean, versicolor and so on. But we can see here that the output isn't actually 1, so we're less certain. So again, petal length, petal width, push it in that direction. But there is a feature here which is negatively contributing to that. So saying that, oh, actually this reduces our confidence in this classification. It doesn't actually give a label for that, this diagram, annoyingly, but we can infer from process of elimination that that's sepal width. And we might you might think that although these are local explanations for individual instances, one question might be, well, if we can explain all instances locally in this manner, can we combine those to get some idea of how this model is operating globally? And we can do that as well. I don't think these diagrams are particularly fantastic. They're quite confusing, but they do demonstrate the principle. Where we can see all 30 instances in our test set, and this is probably most useful if we pick a particular feature. So if we pick petal width, what this is essentially telling us is that the boundary for changing the classification is between 0.4 and 1.0, and it's that space where we're potentially uncertain between the two different classes. So that's a very quick overview of what Shap can do on a simple data set. It's maybe worth just saying, just showing the repo here, and the reason I show this is that we can see that it's very, very active in terms of issues, pull requests, stars. It's a very popular technique that's been used very, very widely, as is LAIV, and I really think that's been a change recently, where more and more people are getting interested in these technologies. I'm just seeing there's a question there for Shap. Whose job is it to annotate the training set with semantic features, ideal petal width, etc., supervised, unsupervised learning of semantics or of semantics of features? I don't know, Rob. Sorry, I know that it takes the labeled data to generate the explanation, but the exact mechanics of that, I'm not too sure about, or beyond the summary that I gave in the slide before.
But maybe the answer Rob is looking for, that it's pretty automatic. So giving a data set and given any model, what we saw, these ideal values of features, they were generated automatically by the tool. At least the figures we saw in Michael's demo, they were not given by someone in advance. This is something the tool works out just by looking at the data and the model. Michael,
Exactly.
Probably Rob
right.
is asking, how automatic this is.
Yeah, if that was the question, then I misunderstood it. That is automatic. If you have any labeled data set, Shap and LAIV are able to generate explanations of that without actually needing to know anything about the model itself and how that works, which is useful. That explanation might not be totally robust, as we'll see shortly, but it does give you an explanation.
Rob, did this answer your question?
Yes, I guess my question then is, if it's just based on the annotations, are the annotations, what's the granularity of the annotations? Is it about the width of a petal, or is it simply this is a flower, and somehow the model is learning what a petal means and what the width means? So, well, what's the granularity of annotation?
Yeah, I think the mistake I've made here is not going into explaining what the actual features in the iris data set. So the data set, I'll tell you what I'll do. I'll just log out quickly what that looks like, the original data. So this is the data we're working with. If I just show you what the training data looks like. Getting into live coding now, very dangerous, but let's see. So this is what our data set looks like here. So we have these four features: sepal width, sepal length, width, petal length, and petal width. And we also have the y-axis just tells us three different types of flower. Oops.
Okay, so that answers my question. So the actual training data set has the information about these semantic features.
Exactly. Yeah. So I missed enough. I thought you were looking for a more technical explanation of Shap, but yeah, no, exactly right. It's just it's a standard labeled data set it's a supervised classification problem, and although these are numbers, these actually map to different varieties of iris flowers. Yeah, actually, no,
Thank you.
problem. Thanks for the question. Yeah, no, that's helpful.
It's an important point. That's what it's called a nominal data set, when every input feature intuitively has some meaning, unlike, for example, pixels, when we don't assign any particular meaning to any pixel. So here, in a way, in the data set itself, there is some semantics of features, which is not always given in machine learning.
Exactly. Great. Okay. So let's carry on with this then. So now we've seen that demo, and I'll just before I go into that, I'll just highlight on this slide. Let me get my pen working again. So we've got we use this to generate this local model here, and remember, we're only trying to explain one specific instance here. We're not trying to. We can see this split here kind of roughly mirrors this boundary in the input space, but if we're over here somewhere, that obviously doesn't tell us anything about what's happening. And actually, even within on this example, even within this on this boundary, we can see down here it doesn't actually mirror the classification, which are these two colors in the background. So from that, we can kind of say that, and there's this quote from this paper, which is an excellent paper actually. I'd really recommend. I really recommend, if anyone's interested in this, reading this paper by Cynthia Rudin. Now, there's a proper reference at the end, but the quote is, explanations must be wrong. They cannot have perfect fidelity with respect to the original model. If the explanation was completely faithful to what the original model computed, the explanation and the original model would be one and the same thing. So hopefully that intuition makes sense. I wondered if we could formalize that notion of fidelity, and we can to a certain extent using Lipchitz functions. I'm sure people are probably familiar with these, but I'll explain these because I wasn't familiar with this idea. So essentially, all these are doing is measuring the rate of change of an output with respect to an input, with the constant c providing bounds on that rate of change. And Wikipedia is very helpful as ever in understanding that, where we have this diagram where this diabolo shape that's moving across actually represents the gradient of this represents that value of c, and we can see that the gradient of this function never actually exceeds that value of c. So it's a useful method of explaining how stable a function is. Let's look at the question. Have a look here. What is meant by wrong? Is an approximation of the model, sir. So it's yeah, good question. Good question. I suppose I actually come on to that in a couple of slides. The idea of when we say an explanation that's not robust, what do we need to be quite careful with what we mean by that. But yeah, your point is valid, I think, Luca. In that, I'll just go back. Getting a bit of a muddle here with PowerPoint. Sorry. But it's not. It isn't wrong. I suppose that's right. I suppose provided you understand the what this is actually giving us, which is a locally faithful model only, then it does what it sets out to do. However, there is clearly going to be a space where that's not faithful to the original model we're trying to explain. If that helps at all. So I'll talk about why this idea of Lipchitz is useful for explainability robustness. And the reason for that is it gives us a way of actually measuring explanation stability to input changes. And we can see a very quick example of just the sort of thing we mean here. So we see an image showing a linear classifier here, a really simple linear classifier that just uses the values on the x-axis to classify. And again, it's the background colors that represent the two classes. Let's call that class 1. Let's call that class 2. And we can see these we've got points here with these bar charts, which are the explanation for that result. I think this is actually using LAIV behind the scenes. But we can see the explanations are quite stable here. If we look at a particular region, we can see that all the explanations here are identical, and the same in our region 1. However, if we we'd expect that given it's a very simple linear model. However, if we look at a slightly more complex model, so a 2-layer neural network, we can see that the classification result is now nonlinear. So we get these sort of contour type boundaries, and we can see that there's also far more instability in the explanation result. So for example, if we look at these 2 points here, these 2 points are very similar very close in the input space, but the explanation actually looks quite different. Here, the green bars are the contribution of the x-axis feature, and the purple bars are the contribution of the y-axis feature. So don't read too much into the specific data, but that's kind of what we're talking about when we say explanation robustness. So we only to use Lipchitz for that, we need to just be clear that we only care about stability within a finite neighborhood. We'd actually expect a large difference for a large change. So we introduce this constant to indicate the size of the neighborhood that we're interested in, and then apply the same method of working out this constant. And the results of this, this is obviously a little bit out of context, but what this paper does is take different data sets. These are different data sets from the UCI library of machine learning data sets, and it essentially shows, and this on the y-axis is this Lipchitz constant on a logarithmic scale. And the interesting thing here is we see that there's a huge difference between different data sets, and indeed within different data sets. So this range here is the difference between different instances within a specific data set. And in terms of what that actually looks like, so if we take that to be a value of about 10 or 15, what does that actually look like? Well, we can see an example here. If we look at the right-hand side of this, we can see we've got two. This is using the Boston housing data set, house prices data set, to give us an example. But we can see here that small changes in the input, and you'll note that the changes in the input here are quite small. So there's certain inputs here are changed by a 0.1. I think there's maybe two or three changes here. But we can see that's had quite a large impact on the explanation. So these top few fields have changed quite significantly in their importance for the explanation, and as have others too. So it's a very quick summary of the work in this area. But the broad conclusion is that, as I think you alluded to Luca, in the comment, can we trust post hoc explanations of AI models? Well, probably not, and that's not unexpected given how they work. They only attempt to be locally robust. But there's this interesting question that I'm sure a number of people in this group having seen that, which is what about when the model itself is not robust? So we see here the explanation changes when we change the input values, but who's to say that that isn't because the output's changed? And this paper is very good, but it kind of brushes over that a little bit. And that question of when we have a model and an explanation, both of which aren't robust, is an interesting question, which we're going to touch on a little in the next couple of sections. I'll just check the chat. Priya's helpfully given an update on her question. So my early question about user explanations are with respect to a user stroke domain expert. And so where I was wondering whether this is factors, is that a priori knowledge to be assumed? It's a good question. I mean, so this is the idea that explanations can look completely different, or a good explanation rather can look completely different depending on the audience. So if I'm a developer and I'm looking to debug a machine learning model, I'm probably quite interested in the detailed weights and biases of a neural network, for example. Whereas if I'm someone using that model in to make credit decisions, say, I'm probably more interested in which of the features which have been used to actually produce that prediction. And I think that broadly, this isn't factored in too much to answer your question, Priya, into this, but there's a kind of broad assumption in this talk that we're more interested in that kind of feature level explanation. So which features are the more important for us in making a prediction. But it's a good point that other methods of presenting that are available. I hope that answers your question. And are there any other questions while we're on this slide? Great, thanks, Priya. Okay, quite conscious of time here, so I better get cracking. So yeah, this next question. So can post hoc explanations be fooled by adversarial attacks? So let's consider this. I'll skip over I just wanted to just be clear what we mean by an adversarial attack in this context, because normally in the machine learning literature, when we see the term adversarial attack, we mean something like this, where we actually are able to alter the classification of an input using some kind of perturbation. The most famous of which is this FGSM approach. And this might look like white noise here, but actually this has been calculated to give the worst possible impact on the correct classification. And so we go from predicting this as a panda to predicting it as a gibbon with very high confidence, and without any visible change in the in the image. As a very short tangent, I did actually see this. I did actually see this a couple of days ago. This term I'd never heard of before, a typographic attack, it's called, where we actually append text onto an object, and because most classifiers are really good at recognizing text, this goes from saying, yeah, this is definitely a Granny Smith apple, to saying, yeah, we're absolutely certain this is an iPod, which I thought was quite funny. But also there's an interesting point that, you know, I read this in the Guardian, not on Hacker News or something like that. You know, so the idea of adversarial attacks on classification is quite well, I wouldn't say understood, but quite widely known about. So forgetting about that then, so what do we mean when we say an adversarial attack on an explanation? So there's kind of two, my mental model for this is to divide it into two categories. Number one is actually manipulating the input in some way to alter the explanation. So this is kind of similar to the adversarial attacks on classification, in that we apply some kind of perturbation to this manipulated image, and we go from and this I should explain is showing us which pixels are the most salient or relevant for the classification. So we identify this as a dog by its, you know, pointy ears and its wet nose, for example, which makes sense. Whereas in this manipulated image, we can see we've got some arbitrary text, which is quite a cool demo. So that's the first category. The second one is actually, to me, it's kind of more interesting. It's actually, can we build something that's build a classifier that's globally adversarial in terms of explanations? And but before we actually get into this, there's an interesting real world parallel, which is it's not really a computer science one, but it's this Dieselgate thing from a few years back, and people probably know this, but I'll explain it quickly anyway. So VW cars, and I think others as well actually, were trained in some way to recognize when they were being tested for emissions, and they were so I say taught, you know, it's not a person, but that they knew to behave differently in that circumstance. So sacrificing performance and probably other things too, in order to cut their emissions. It's, you know, incredibly naughty, really, you know. But the interesting thing there, and the parallel with what I'm about to show, is they had a way of recognizing when they were being tested, and the parallel with machine learning is, can we look at models where we actually can tell, can we build a model where it can tell when it's being asked for a genuine prediction versus when it's being asked to explain itself? Because going back to your question earlier, Rob, both of those requests are using the same data. You know, we're not doing anything magic with the data to set it up for explainability. We're using that same, you know, that same iris, petal length, sepal width data for both. So can we do something similar? Yes, we can. And before I get into demo, I'll just have a quick look at these questions. Oh, Fraser just shared a link there to the clip attack. Which is that's the typographic one, is it? Yeah, I wouldn't mind reading that actually, about reading that in a bit more detail. Thanks for that, Fraser. So I'll better whiz through this. Actually, I'm conscious I've completely overrun here. But this demo is about building this adversarial classifier. And I do actually explain how this works in the next slide. So I think in the interest of time, I'll just skip through this. And while that's running, this is based on well, it's not based on it. Basically, shows the work of some researchers at Stanford, who chose to focus quite explicitly on racial bias in models, and specifically using this a data set called the Compass data set. Which is one that's used to predict the States, it's used to predict risk of reoffending, and it was shown a few years ago that it was quite brazenly racist. And so the focus on bias is a real kind of a real problem to be solved. So I think that's why they've decided to do that. But what this is, what I think I probably need to just explain a little bit of this code. What we're essentially doing is we've got this compass data, and I'll maybe just I think it's helpful to actually show what that data looks like, isn't it? After the iris example, so let's just actually try and show that. Oh, we don't have the column headers there, do we? I suppose that doesn't matter, but what we are doing is we're adding to this data set a new column which contains completely random data. So we call it unrelated column here. And we do that to make sure that that column has no correlation with the data that is actually used for the prediction. In this next section, we set up two separate classifiers. Now, these classifiers aren't doing anything clever. They're not even simple linear models. All they're doing, our bias model, is simply homing in on race as a method of predicting, on a method of giving an outcome or giving a reoffending risk. Whereas this innocuous model is using that unrelated column. Sorry, the unrelated column that we added and generated random data for. So clearly these two models should behave quite differently. So we do some usual test, train, split, and normalize. And then what we can do is we can train an adversarial model in a way that I'll explain in a moment. But what we can do is we can actually explain both of these classifiers, our bias classifiers and our adversarial classifier. And we can see here that that with the bias classifier, this sensitive attribute of race is used entirely to generate a prediction, which is what we'd expect, given that we've told the classifier to do that. However, our adversarial classifier is telling us that it's using this unrelated column as the most salient feature. But actually, both of these classifiers are, when asked to make an actual prediction, are behaving the same. It's just the explanation that's differing. So I'll go into the explanation of how that works. I'm just having a quick look at the chat here. You're right.
Yeah, if you have a look at that paper that I've linked to, that whole thing with the algorithm for Compass supposedly being biased was fake news. The group that I worked with at Queen Mary, we ended up publishing a paper. I've just linked to the sort of preprint of that paper there. The fact was that while the people who built Compass claimed to have removed everything to do with race from the way that the algorithm worked, what it was the minute that you have any field within that data set that correlated with poverty in the area where the data set was being used, of course, you were naturally going to end up with more Black Americans and Mexican Americans being picked up by it. So the algorithm itself, while the media put out the headlines going, oh, it's racist, the algorithm itself was just looking at poverty and using poverty as the surrogate factor for making the decision.
Yeah, interesting. I'll be keen to read that paper. I mentioned it more because just to make the point that whether or not that example holds up, I think most people would agree that bias and fairness in machine learning is is a problem. You know, we see examples of that. You know, we see numerous examples of that.
The fact is
and it's due to, sorry, go on, Scott.
Pure machine learning, and Norman Fenton, Professor Fenton, and I give a talk on it. Pure machine learning on its own, without expert and causal input, is doomed to fail. And every time you look at pure machine learning models, in the end, you find a reason for why they should fail or why they do fail.
Yeah, interesting. I think I think Priya's in this chat is, yeah, bias in the data is a problem too, and I think that's it, isn't it?
Well, that's the Priya's right. That's the exact reason they fail. It's because when you've got a machine learning model and it's picking up from one of these data sets, like the one that they use for Compass, what the machine learning model can never do, what you need the expert to do for you, is tell you what are the latent variables. So, I mean, there's a brilliant example whereby it was published somewhere. There's a website that publishes all these things that are, you know, these correlations between stuff. And one of them is the correlation between consumption of expensive Parmesan cheese in Italy and, you know, the fact that people have, lots and lots of people are graduating from university with degrees. And the two lines almost identically match and they go up together. And so, you know, it was sort of erroneously reported that, you know, doing a university degree meant that you bought more cheese. Well, the two things, it was the latent variable of income that was actually the thing. But you can't have a machine learning model that looks at the two data sets and goes, you know, cheese consumption and university degrees, and puts that together. All it does is puts the two together and go, oh, they look the same, so therefore there's a relationship. It couldn't, the machine learning model could not then find the third variable, which was the increase in viable income. Yeah, that's spurious correlations. Brilliant website.
Yeah, I've seen that. Yeah, no, I mean, I agree with all of that. The only point I was just essentially saying, you know, bias is a thing, and I think that I think this idea, yeah, I think I do wonder actually whether you know, the explicit focus on bias with this work by these guys over at Stanford is, I wonder if it's that helpful. I think the more interesting thing here is that we can manipulate these models to artificially alter explanations in general, and you know, the fact that it can be used to hide bias behavior is just one aspect of that. But no, thanks, it's a useful point. I'll go back to my slides. So how does this work? So really quick explanation. So remember that LAIV and Shap, these explainability tools, they work by generating perturbations of the original data, and the crux of this is that those perturbations are often off the manifold. And my understanding of the manifold, that probably isn't terribly isn't hugely formal, but it's basically the grouping of the inputs. So we can see here it's that same Compass data set, but reduced to two dimensions via PCA. And we can see that we can quite easily group the original data versus the perturbations due to those perturbations being off the manifold. And that means that we can quite trivially build a classifier to identify when it's being asked, or to separate those perturbations from the real instances, and that allows us to quite easily train an adversarial classifier, which first of all identifies whether the instance is real, so whether or not it's on the manifold, and then it wraps two different classifiers. The first of which is used, which is I will call it a bias classifier, but we'll call it a what should we call it? We'll call it what's the word there? We'll call it one that hides classifier that hides the true explanation, and this can be our true. This can be our true classifier. So, so this is the one used when making. I've got the wrong way around, haven't I? But this f of x is used when we're making a natural prediction, and this is the one that that gives the true behavior of the model, whether it's biased or otherwise. And this psi of x is the one that gives a false explanation when explainability tools are used. So quite an interesting technique, and quite simple, I think, to understand and implement. So the broad conclusion is that can post hoc explanations be fooled by adversarial attacks? And I think the answer to that is yes. There are other techniques available as well that I've not actually mentioned. And is this a real world risk? I kind of think it is, for a few reasons. Model internals are often hidden. There's a history of biased classifiers, and yeah, as Scott and others have rightly pointed out, we need to take that with a bit of a pinch of salt. But there are examples of that. And after this Dieselgate example I mentioned, and numerous accounting scandals over the years, we can see that there is occasionally an appetite to obscure information from auditors or regulators. And the last point is that an explanation, even if it's wrong, does have the ability to increase trust in a model. So we do need to be very careful, I think, with explanations that aren't totally robust. So I'll just have a quick look at the chat, and feel free to ask any other questions. Video original talk. Yeah, thanks to this chat. I assume someone will copy this chat. Actually, I guess I can do that, can't I? I'll post that on the Slack afterwards. So I'm quite keen to look at some of these links. Does anyone else have any other questions?
I have one. What are you planning to do for your dissertation then? What are you planning to investigate?
What an excellent segue into this next section, Matthew. It's almost like that was a plan.
Sorry, I thought that was the end of the talk.
No. There's more. I'm afraid this is the last bit. I mean, this is really short because this is a work in progress, right? This is what I'm planning to look at, and there's a few different there's a couple of different techniques. I've said three there. The first is this is more of a there is this argument that we see that we should be moving towards more inherently interpretable techniques. Obviously, that's clearly not practical, and there is a need for robust post hoc explanation techniques. So the two kind of directions I've got there are first of all, and I'm really interested in people's thoughts on this. The first is a heuristic-based approach. So the obvious way of looking at this is to apply multiple explanation techniques and evaluate the difference. And the naive way of doing that is, well, we'll look at the result itself. And if one explanation technique is saying that the salary is the most important attribute of something, and another one saying it's actually location or number of children or something, we get a bit of a clue about that the explanation might not be, one of those explanations might not be robust. I think another interesting aspect of that is to look at this Lipchitz constant, which, remember, tells us how stable the explanation is. Because I think that if we have one model which is extremely stable, i.e. has a low constant, and another which is extremely unstable, i.e. has a high constant, again, it's a bit of a clue that something might not quite be right. And I think that this one hypothesis I have is that this might get us some way to solving that problem of there being a model that's not robust and an explanation that's not robust. Because if we had a model that was robust, we would expect at least one of these constants to be quite low. So that's kind of my theory there. Whether that will hold up, I'm not too sure, but I guess that's the fun of it. The issue there is it's not a formal guarantee of robustness, and given we're in the lab of lab for AI verification, we can probably guess where this is going next. It's a more formal verification based approach. So admittedly, this is, I think, as I've done this research, I've become more and more interested in the links between formal verification, and I've just started to look at Marabou, which is SMT solver, which Matthew's assured me scales quite nicely. So I hope that's true. But there's a few ideas here. I mean, one is to look at whether so we've got an explanation and it tells us certain features are more salient. Can we apply verification techniques to assert that that's actually true? And my mental model for that is there's this epsilon ball idea that where we look at an input space and evaluate, is the output in that input space, is it in the area we'd expect? But can we kind of stretch and manipulate that input space if we know that certain features are supposedly less or more important? So that's that. There's verifying the surrogate model as well. Does that mirror the parent model within some kind of definition of locality or neighborhoods? And the third is really an extension of the first point, but it's to focus specifically on bias. If we keep our instance constant and focus our validation efforts on sensitive characteristics specifically, does that tell us anything useful? And of course, we need to be a bit careful there, because there might be spurious correlations. We just need to take that with a bit of a pinch of salt. So they're the ideas. So yeah, I've got a few thoughts on how to do this, but very interested in people's feedback. And the overall conclusion, and this is the last bit now, Matthew, is I don't know to what extent we can gain confidence that explanations are accurate. If you'll have me back, I'll more than happily come back and do another short talk again in the summer with the results of this. But I do think that the nub of this is this problem of the model and the explanation both being unstable. It's a really challenging one, because that means we can't just look at the robustness of an explanation. And I do think that formal verification techniques do have promise in solving this problem, although admittedly I have made that statement without too much empirical evidence at this stage. But we'll see how we get on with that. So here are some references which I'll put up in case anyone's watching this back and wants to pause it there. I particularly recommend this Cynthia Rudin one, and also the one about the use of the Lipchitz constant ideas. They're probably the two I found most useful and interesting. So thanks for listening, and sorry to overrun slightly. So we've got Scott. Here's another example of the compass system having data bias. Thanks for that, Scott. Yeah, I'm really. There's a good chance. Scott, are you on the Slack for this group, the AI group? Because I'd quite like to have a chat with you about this at some point. It sounds like you've got a lot of insights into this.
I am. I don't very often go on there, so you're probably better to email me first.
Okay. I might well do that, because it's very, very interesting.
Yeah, I'm actually. I mean, because I was on my iPhone before, I didn't get introduced at the start. I'm the postdoc fellow at Edinburgh Uni. That's technically I'm in the law department, because of course I have law degrees, but at the same time I also have a PhD in computer science, and I specifically did it in things like causal Bayesian type modeling and AI. So